But let's think about continuous convolution in the context of problem number 4 in the in-class test. So here we use the MGF technique. Let x and y be independent exponential random variables with parameter beta, which is the mean. Use moment generating functions to determine the distribution of the random variable x plus y. So you multiply the moment generating function of an exponential by itself, effectively, is what you do. And then use the fingerprint theorem. So what you should have done, and I think most of you got this right, was to look up the exponential MGF. Exponential MGF 1 minus beta times t to the negative 1 power. X and y are they both have the same distribution and they're independent. You could write x comma y is exponential with parameter beta, which again is the mean, and independent, implies that the moment generating function of x plus y is the product of the moment generating function of x with the moment generating function of y. But those moment generating functions are the same. They're both 1 minus beta t to the negative 1 power. I'm not saying x and y are the same random variable. I'm saying they have the same distribution. Their observed values could be different, though. They're modeled by the same PDF, but that doesn't mean they equal each other when you observe them. In all likelihood, they're not equal when you observe them. But they have the same distribution. They have the same moment generating functions. And there's the moment generating function of their product, which is not exponential because it's not a negative 1 power. But it does fit this one. Alpha is 2, and that's gamma. So it's a gamma distribution by the fingerprint theorem. X plus y is gamma. Not with any old alpha, but with alpha equal to 2. And beta is the same beta as before. So that's definitely the easiest way to go to figure out the distribution of x plus y. What would its PDF be, by the way? It would be this when you take alpha equal to 2. And beta is arbitrary. So the PDF of, let's call it W, equals x plus y. Would be 1 over capital gamma of 2 times beta squared. It's beta to the alpha in general. Times x to the alpha minus 1, which is 2 minus 1, e to the negative x over beta. Capital gamma of 2 is 1. So this is 1 over beta squared. 2 minus 1 is 1. There's the PDF. Oops, I should use a W instead of an X. Sorry. Yeah. Sorry, this is a W. 1 over beta squared W e to the negative W over beta. Can we derive this PDF some other way? Like the CDF method, for example? The answer is yes, but it's not easy. Let's use the CDF method to derive it. So far, I've just used the table, right? I haven't derived this. I've just used the table and the fingerprint theorem. and this fact. Oops. Probability that capital W is less than or equal to little w, but capital W is x plus y. But how in the world am I going to go any further? I mean, I do know x and y individually are exponential. But usually at this point, you solve for x or y on one side of the inequality. And I mean, I could do that here, but is it helpful? Because I'd still have a random variable on the other side, not a non-random variable. We actually did do a problem like this 3 weeks ago. Remember it? With a uniform distribution, and I shaded some areas in a square to help us figure this out. Unfortunately, you can't. Yeah. Can't replace y by x and say this is 2x. We need to do something similar to what we did 3 weeks ago. Except x and y are not uniform anymore, they're exponential. And we can't just think in terms of shaded areas anymore, because with uniforms, the PDF is constant. So probabilities can be found by finding areas. With exponentials, the PDFs are not constant. But it's still going to be useful to think about areas, or at least shading regions. Draw a plane. Should I label the axes with capital letters or lowercase? Probably it's more traditional to use lowercase. What I need is I need the joint distribution of x and y. That's what I need. Chapter 5, which is the chapter we didn't spend much time on so far. I need the joint distribution. And I need the assumption of independence to help me figure out the joint distribution. And to figure this probability out, I'm going to use the joint distribution and integrate over an appropriate domain in the plane. W is fixed, say W is positive. X and Y are exponential. It makes sense to restrict your attention to where W is positive. The line little x plus little y equals W is the same as the line y equals W minus x. It's a line with a slope of -1 and a vertical intercept of W. And in fact, because the slope is -1, the horizontal intercept will be W as well. And it's this region that I need to integrate over, because that's where x plus y is less than or equal to W. And I can stay in the first quadrant because x and y both need to be greater than or equal to 0 as well. So I don't have to go down into the other quadrants. But what is the joint PDF of x and y? Our book would label that f sub xy of little xy. Independence is needed to figure it out. Remember, and I said to know this for the test in case I put a true false or multiple choice question about it on the test. And I think I did, except I wrote it in words instead of an equation. X and Y are independent if and only if the joint density is the product of the marginal densities. That was a true false question written in words. And the answer was true. That's the definition of independence, not a theorem to prove. This is what independence means. And so I'm going to use that here. This is going to be independence. This will be the product of the marginal densities of X and Y individually. What are those? You got to look it up in the table again, exponentials with mean beta. I hope you maybe even remember it without looking it up. It's this for X and the same kind of thing for Y, except with a Y. And so the joint density is 1 over beta squared, e to the negative, you could write it as X plus Y over beta if you like. But it might actually, for the purposes of integration, be better to write it as separately, as the product of 2 exponentials. That might be better to write it for the purposes of integration. Either way is okay. So that's the joint density. That's the thing we need to integrate over such a region to figure out this probability. So let's do that now. For an arbitrary positive W. But just in your mind, you got to just realize W is fixed, some fixed positive number when I do the integral. Though at the end, when I finish the problem, then I say, hey, now W is a variable. Whether something's a constant or a variable is all in your head. It's all in how you're thinking about it. When you do the integrals, pretend W is a constant, then get an answer, but the answer is going to depend on W. And then you say, hey, now I'm going to think of W as a variable. So this is a little practice in multivariable calculus, actually, which is not technically a prerequisite for prob and stats. It's not, therefore, not technically a prerequisite for this course. But we do a little bit of multivariable calculus anyway. In prob and stats, we mostly try to keep our double integrals to rectangles, though I think I do, at least in class 1 triangular example, kind of like this, except probably with particular numbers. W is an arbitrary positive number here. How do I integrate over such a region? It's a double integral. If, for example, I take the outer integral to be with respect to X, which is the way I usually think about it, the outer integral with respect to X, the inner integral with respect to Y, right? That. You always want your outer integral to be from one constant to another constant. W is a constant when I do this integral. X goes from 0 to W. The inner integral, when you're not integrating over a rectangle, is going to, in general, integrate from some function of X to some other function of X. For any, here's the way I think of it, for any fixed X, like say right there, what does Y vary between? It varies along this line from the second coordinate of this point to the second coordinate of that point. The second coordinate of the first point is easy, it's just 0. The second coordinate of this point depends on X. How? That's how it depends on X. It's W minus X. That's the second coordinate of this point for a given value of X, because it's on the graph of Y equals W minus X. One over beta squared, e to the negative X over beta, e to the negative Y over beta. If I do this double integral, that should be the CDF. And before we do it, just realize, think about it here. In the end, the X and Y are going to go away. They're going to be integrated away, and you're going to be left with something that only depends on W. Do the inner integral first, leave the outer integral as is. Actually, I should be able to predict the answer for the inner integral. Should be simplified to that. PDF of X will be the same as the marginal distribution of X. Though it's possible it could be some modification of that. Let's just see what happens. So I'm going to integrate first with respect to y. The inner integral here is with respect to y. Treat the beta as constant, treat the w as constant, treat the x as constant. Y is the only variable. So I got to integrate e to the negative y over beta. Can I do that in my head? Antiderivative. That would give me an extra factor of negative beta. Let's leave this part as is. 1 over beta squared, e to the negative x over beta. That's just a constant. Integrate e to the negative y over beta. That should give me an extra factor of negative beta, because if I differentiate this with respect to y and use the chain rule, I'll get an extra factor of negative 1 over beta, which will cancel with that negative beta to give me 1. Y goes from 0 to w minus x. Yeah, we are going to get the w minus x involved in place of y. What will that do? Let's just see what happens. First, replace y with w minus x. Which I can bring the minus sign through and write it as x minus w. Is that worthwhile doing? To do? I'm not sure. Let's just do this initially. And then I have to subtract what I get when I replace y with 0. Does that look good? Check it over in your mind. That'll help you stay awake anyway. I think it's good. E to the 0 is 1. This is just a plus beta. I didn't try this example before class. It's turning out a bit more complicated than I was hoping, but tell me where to stop my pen. Yeah, this is multiplying times the whole thing. Yeah. Of course, the betas cancel with the beta squared to some degree. So I get really just 1 over beta. And what am I left with? I'm left with, I guess, 1 minus. Oh, this is turning out not so nice. I can bring the 1 over beta in front. Maybe I'll go ahead and do that. But it seems like I've got the integral of the difference of two things. This times 1. Yeah, okay, if I multiply this times this, I do get a little cancellation with the exponents, because a plus x over beta cancels with the minus x over beta to give me 0. It looks like it's just e to the negative w over beta. If I have not made a mistake. So that's nicer than it would have been. So I'm integrating that with respect to x, and this is a constant. Hanging with me? I know it's not super exciting. The excitement comes in hoping that the answer turns out to be enlightening. But now we're trudging through all the calculation details and hoping not to make a mistake. doing this final integral now. And again, that's just a constant. So I multiply it by x. X goes from 0 to w. Be careful. Negative beta e to the negative w over beta minus, I'll put the w in front, w e to the negative w over beta. Now plug in x equals 0. E to the 0 is 1. You get a negative beta times 1. And that becomes 0. So, boy, have I made a mistake here. The CDF, if I multiply the 1 over beta through, the two minuses times make a plus. I get a plus beta here, but then times 1 over beta is just a 1. This beta times that beta cancel. I get a negative e to the negative w over beta. And then plus or minus 1 over beta w e to the negative w over beta. This is evidently the CDF when w is positive. I'm almost done. Now differentiate it to find the PDF. And I think it will simplify nicely. I think. Differentiates to 0. I get a plus by the chain rule. This. I do need to use the product rule here. First function and second function. Derivative of the first is 1 over beta times the second. And those are going to cancel. And then I get a ultimately plus 1 over beta squared. This is looking good. Those cancel. 1 over beta squared w e to the negative w over beta. I wrote that equation 20 minutes ago. 1 over beta squared w e to the negative w over beta. Wasn't that worth it? We did the convolution to get the same answer. Of course, the moment generating function technique is easier. Although that's hiding some difficulty because the fingerprint theorem is hard to prove. This is a continuous convolution. Essentially, this final function that we got, you could say it's f star, or you could say it's f sub x star f sub y of w, where star is the convolution operator. But what does that mean? What does the convolution operator do? Let's look it up online. I'm afraid if I write it down from memory, I'll get it wrong. I do have a book that I was going to bring, that I forgot to bring, that's got it in there. Oops. Continuous convolution. Okay, here it's written as a single integral from minus infinity to infinity. For us, that would simplify to an integral from 0 to infinity. It's not obvious that it's going to give the same answer because it seems different than what we did. Yeah, and I'm not going to take the time to justify it, that it gives the same answer, but it does. Not today. Maybe when we come back. This method though, so yeah, maybe we'll justify this when we come back from break. This method of doing double integrals over triangular regions generalizes even to situations where the variables are not assumed to be independent. Because effectively, instead of using this independence assumption, we just work with joint PDF. In that context, we're not really doing convolution anymore, but it's a similar kind of method. It's just that the joint PDF is going to have some other formula. It's the way you deal with it when the variables are not independent. You do need some kind of model for the joint PDF that you hope still seems reasonable and valid. And that's another question. But assuming you've got some joint PDF that is not the product of the marginal PDFs, you can still essentially do the same method. But this method with independence is essentially doing a continuous convolution without getting into the details about why.